Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. It is another lighting weekend here. Last weekend we sort of got everything working that's the basic infrastructure for doing some kind of lighting pass. We still don't know exactly how we will end up doing it. We have a couple things that we're working on right now for possible ways that the lighting will play out. But regardless of what that way is, obviously we needed sort of this infrastructure where we could take renderings from the game, feed them through a lighting system, and have ways of iterating on what was in that lighting system to produce lighting. Right now, all we're doing is very, very simple blurring of the lighting. We're not actually bouncing it around like we would like to. So we haven't actually gotten to implementing the lighting transport part of things. So that's one thing we have to do. The other thing we have to do is we don't yet pick up the results of the lighting and feed them into the game proper. So what I'd like to do today is just finish that part up so that we have a complete lighting pipeline operating where we can take the lighting, it can come into the game, come into the lighting system, bounce around, produce a lighting solution that we want to use, and come back out into the render that's there in order to produce whatever the final lighting is, right? So that's what we want to do here. And so I'd like to kind of play around with that a little bit today, just kind of get a fake version of that working, meaning the lighting transport will still be fake. But the rest of the pipeline will be effectively real. Now, there's a little bit of an issue with this, which is to say that right now in the lighting system, we're only computing lighting on one layer, if you will, right? There's 4 depth peels that we produce in the game, and we only produce the light currently on that top level of the lighting. Of the peel. And the thing that we probably want to move to in the future is we probably want to have a way of using the lighting information from all of the depth peels in order to produce lighting that can bounce around behind objects. This is one of the big drawbacks of screen space solutions to a lot of lighting problems that you see. Is that you can only compute screen space lighting solutions for geometry that's at the front. But if, like we have, you are computing depth peels for some other reason, and we are computing depth peels because we need to do blending in an order-independent way. We want to do blend composition. Well, since we have all of that information, it means that we can do light transport between 4 layers of geometry in the scene, not just the front layer. So eventually we also want to move towards that, as well as moving towards real light transport. We want to sort of move towards something that takes those slices into account potentially. So we have that opportunity, and we just don't know whether or not we're going to be able to take advantage of it in any particular way. But an example of how to take advantage of that, and we talked about this when we first started planning the system, would just be to say, look, why don't we just process the lighting on 4 layers at once, where we just know that we've got essentially an iteration over 4 textures for each depth, and we just do the lighting calculation 4 times every time, right? So anything that we were going to do where we would accept light from 1 texel in the past, we accept it now from 4 texels, where each texel is a different one of the depth peels and has a different light source. So that's an example of how we would go about using this information more concretely. And effectively what we're doing there is we're effectively saying, let's use, we're effectively doing sort of voxel cone tracing, or one of those other voxelization-based lighting schemes, because effectively what a depth peel is it's a sparse voxelization in Z, right? It's a dense voxelization in X and Y in the sense that we cover the whole screen projected outward, but it's a sparse voxelization in Z because you only are taking samples where you hit the geometry. So it's very efficient in that sense compared to a dense voxel or a voxel that has to be regularly subdivided. So even something like an octree, in Z would be much better than that, because in Z we are literally only concerned with the actual places where the geometry exists, and that's much better than a voxelization in terms of efficiency of elements, right? So that's the sort of stuff that we have to think of going forwards. And so I don't think there's much left to say about it. We just have to sort of do the elbow grease of getting all this stuff ironed out, which I'll go do now. One further thing I wanted to mention is that I don't know whether multi-grid lighting is going to work out, or whether we're going to have to sample the lighting in a less up-down sort of fashion. And if it turns out that we do have to sample the lighting differently than that, then one thing that we're going to have to do is we're going to have to be able to sample from multiple resolutions of our textures at the same time. And in order to do that, one of the things that we would have to do in order to make it efficient in the shader is to switch to using actual MIP maps instead of separate textures. So one thing we might also want to look at today, if we have time, is seeing if we can get our current system to just work with, instead of one texture per MIP level for every one of the lighting textures we want to store, having just one texture and having it actually have MIP maps. I would like to move to that regardless. Like either way, it would be nice to move to something like that eventually. I just don't know how effective that's going to be on something where we've got a rectangular bitmap like the screen. I don't know to what extent cards will be happy about trying to MIP map that. And so that's really the only real question. Assuming that that works okay, that's probably preferable, because what that allows us to do is, once you have things in a MIP map of the texture, the bonus there, because it might sound like, well, why does it matter? The bonus there is that inside a shader, you can sample from any texture LOD level that you want. So any MIP map in a given texture, you can sample directly from one of those using a particular texture sample call that specifies the MIP map level. So rather than having the card compute the MIP map level based on the U and V gradients or whatever else it wants to do, or things like this, we can sample from specific versions of the LOD, specific version of the texture, specific MIP levels. And the reason that that's so important is that would allow us to do things like, if we want to sample lighting and we know we want to sample far away lighting at a high, MIP, very, very coarse MIP level, and we want to sample nearby lighting at a very dense, very low level MIP, right? One that's one that's fine detail. We can do that in the shader very adaptively. Whereas if we have to specify different texture handles for all those things, then we're ending up binding lots and lots and lots of textures. And we will soon probably flood the 32 texture limit that some cards impose trying to do that. So it's really just a question of putting something, there's no difference between the two in terms of functionality. It's just a question of going with what the card is more set up to do so that we don't run into limitations or introduce artificial slowdown that's not really necessary, because the card is set up to sample from MIPS. It's not set up to sample from hundreds of textures. That's just how some cards work. That's just one of the ways in which they're optimized, and you have to sort of play into that optimization when you can. All right. So I'm going to open up the state of the code right now. Today's day 397, so day 396's source code is what you want to start with. Let's see. Oh, that's not. I want to open it all. There we go. So let's go ahead and run the app as it is at the moment. And if you remember at the end of last weekend, what we were doing is we made it so that we could render lights to the lighting system as part of the as part of the main game render. And so what we did is, you can see here we've got the hero sort of hopping around in the main game render, and you can see how the lighting itself, we sort of took it from that render pass. You can see how the lighting itself now incorporates sort of the hero sprite, which is what we sort of did to hack that in. Since right now our game doesn't, the game code doesn't know about lights and didn't ever try to put any lights in the world. So we just made one up that's where the hero is, and you can see that basically what it does is it assumes that everything within a certain sphere around the hero is a light source. So that's what it's doing right now. And what you can see if we go through the process, you can see that we've got sort of a set of blurred versions of that, right, on the way up and down. And we also have several of these, right? So that hero one is the only one we are capturing right now from the game itself. And the other parts, which are, you know, things like the normals, the surface normals, stuff like that, we're not capturing yet. And so that's, you know, we want to kind of finish up that process of capturing everything into the lighting system correctly. And then we want to go and get it out of the lighting system. But that's really all we're talking about right now. Like, that's all we really are trying to do. So let's go ahead. We're going to need one shader for this, and that shader is just going to be the shader that takes all of the lighting information from a set of depth peel data, basically one peel, and moves it over to the lighting system. And like I said, right now we're just concerning ourselves with the top peel. But in the future, I think we're going to want to try and make that system a little bit better. So one step at a time, since we don't want to overcomplicate our lighting pipeline just yet with the multiple depth peels. And the reason that we don't want to do that is because we don't want to do a bunch of work on something that we don't know whether it's the right solution yet. So once we get our light transport working in a way that we think is reasonable for this game, then that's the time to bring the peels into it, because now we know what we're doing. We can minimize the amount of work we need to do to extend it to depth peels, rather than trying to deal with depth peels the whole way through when we don't even really know how we're going to be bouncing our light around in the first place. We've got I think there was a problem. Someone was saying, well, actually, I guess I should open up the GitHub. I think somebody was saying that we accidentally had a typo in one of our things here, minor copy and paste error. It's 1844, they said. Oops, wrong file. Yes, this is just supposed to be down. There we go. It just so happens that won't do anything particularly different, but it is useful to have that there. Now, one thing we could also decide to do, right, you can see if you wanted to prevent typos like that, we could introduce a little struct with a constructor and a destructor here that automatically does the shutdown on the same thing that you did the startup on, right? I don't know how important that is to do here, but it's just when you have a bug like that, it's worth taking a second and asking yourself, should I introduce a system here that eliminates that kind of bug? How worried am I about having that, right? And so, yeah, you can imagine that that's one thing that you might want to take a look at, right? So anyway, moving on from there, because I don't think I'm going to do that. Let's see here. All right. So what we want to do now is we want to take a look at this compute light transport situation. You can see here that we've got OpenGL begin screen fill stuff happening here, right? We do this. What we did to hack in this process is right before we were going to go and execute the first lighting blend pass, we grab the texture from the depth peel resolve buffer instead. So what this does is this makes it so that we're just cheatily grabbing the color handle, the emit color buffer from the depth peel resolve buffer, which is not what we actually want to do. So we want to stop doing this. And what you can see is if I stop doing that, we get back to just the fake lighting that we had in there. And so what we want to do is replace that fake lighting with real lighting, right? And so what we want to do here is start this with a way to import the results from our depth peel into our initial lighting phase. What that means is we're going to want to do one of these same exact things, right? Where we're writing to the destination, write all frame buffer. However, what we want to do in this case is we want to write to the very first buffer. So the thing that here you can see our source light buffer index, right, and our dest light buffer index, what we're doing is we're starting writing to buffer 1 and we're reading out of buffer 0. And the only person who ever seeded buffer 0 is this fake seed lighting. Well, in order to move past the fake seed lighting, what we want to do is seed buffer 0 now, right? We want to seed buffer 0 with the lighting data that actually came out of the renderer. So here in the OpenGL begin screen fill, end screen fill thing, what I want to do is write to that first buffer. And in order to write to that first buffer, I then need to bind textures to draw from that are not going to come from a lighting buffer. Instead, that they're going to come from is they're going to come from the depth peel buffers. And so what you can see here is we've got these depth peel buffers. They use this OpenGL frame buffer here, and they have this series of color buffers. The color buffers themselves are announced by these three enums here. And so what I want to do is I want to read from those. Now what you can see is that there's emit, there's NPL, there's surface reflect, right? And what we want to do is we want to read from those three, and then we're going to write out to the buffer. So we're going to translate those three into the result. All right. So looking at this, what that means is I'm going to need some kind of a way to access the source, and in this case, it's the we know what it is, right? It's always going to be the depth peel resolve buffer, and we're just going to use buffer 0. So in the future, we may do better than that, but at the moment we are not. We're just going to leave it like this. So what I want to do here is say, okay, I've got an OpenGL frame buffer. That's the source. It's the depth peel resolve buffer. And I'm going to bind the textures out of that. Now, there aren't 4 textures because, remember, this is a different format than the lighting. It's just what the renderer put forth. And so what I want to grab there is I want to grab... oh, well, that's actually true. I take that back. We do actually have one, because we also want to read from the depth handle. So there are actually 4. They're just not the same 4 that they were before. So let's go ahead and put the depth handle first, and then let's do the color handles next. So it would look something like this. And so what we would bind is the depth handle, and then the surface reflect, the emit, the NPL. Now, I'm going to go ahead and use the enums. In case we reorder them, I want this shader to just know that it can get those in this order. So there's those enums. And so this should be able to compile now with no errors because, again, I'm not calling any shader code yet. Now, I got to renumber these here to make sure they go in the right order. Let's make sure that happens. There we go, 0, 1, 2, 3. And here we have our binding. So now what we need to do is basically this program process, which we don't have. Let's go ahead and put that in there. So we're going to want to do a use program again, and we're going to need a program for this. So this is going to be like depth peel to lighting, something like that. Oops. And then I want to do a use program end. So inside here, I need to do an actual draw at some point. So there we are. And all this is, again, is just a full screen fill with a particular program. And that's it. All right. So now all we need to do, we're pretty much set up for doing the importing. All we need to do now is actually get this data into a program, right? So we need to create some kind of new program here. It's kind of like the depth peel resolve, I guess. So I'll start with that as the code we'll use, this depth peel composite here. Let's go ahead and do that. And let's see here. Let's go down here. So what I'm going to do is we'll call this, oops, I put that in the wrong place. I wanted to put it below the multi, actually I put it above the multi-light up is probably the best place for it. There we go. So we'll call this function compile depth peel to lighting. And I guess I don't know that we have the sRGB stuff in here much at all, so this is probably not important. What we do want to do at some point is fix our version numbers to probably be 330 at some point, because if we're going to basically be requiring OpenGL 3.3, there's no sense in not having all of our shaders be 3.3 compliant. There's no bonus to be had by making them old if we're saying that basically we have to have OpenGL 3.3 to run, right? If we're saying we're going to be having that complicated of a lighting. That complicated of a renderer. So I don't think we need any of this just yet. But it does occur to me that the number of times we've sort of been doing this format string bit here, I wonder if that should be systemized in some place where we actually just build one of those to begin with. There's a little bit of fussiness there because you know, we've got sort of the things that want to be set in a particular piece of code in common. But what we could do is sort of have a %s at the beginning that's just the default preamble. Or we could even make it so that there's a thing that gets passed in before that so that the defines that you get here are just kind of shared. And that makes a lot of sense to me, so we probably should look at doing that a little bit in the future. I'm not going to bother right now because I'm right in the middle of something, but that's something that seems like worth doing. So anyway, inside the vertex code here, we don't have a vertex color, and we could use a UV, but I don't think we really want to. I think we want to do a direct write in this case. It's hard to say whether we should use a UV or not. It's just whether or not this sort of stuff is going to be able to be downsampled in any real way without a custom shader, I don't know. So it kind of feels to me like it probably wants to be copied directly. So I suspect that it's kind of not going to want to do the UV stuff pretty much at all. So I think it's just going to be something that straight across sets the position and doesn't do anything else for the vertex shader. And then in the fragment code, we're going to have a number of samplers. So in this case, we're going to have a depth sampler. We're going to have a surface RGB, right? Let's name these the right things. So surface reflect sampler. We're going to have an emit sampler, and we're going to have an MPL sampler. We don't take in any of this stuff, and then we do have out. But the outs for the blend unit color are actually going to be complex now because we are writing to a front-back surface NP. So we do want that to be uniform and correct. So here is that writing. We'll go ahead and put that at the bottom, like so. And we'll delete all of what happens in here because none of it is correct. Now, in this case, we don't really want to sample from a UV anymore. And let me go ahead and get these out. Actually, that's not quite true. So it's going to be more like this. It's going to be more like we have a depth from an R. We have a surface reflect. We have a emit. And we have the NPL. Now from there, obviously, we get a emit RGB, which is from here. We have an emit spread, which is from here. This is the encoding we agreed on. This is our NX. And actually, I suppose I could just do this. Here's our N, right? Well, no, you know what? We need to do math on this sort of in a more unpacky kind of way. So let's do it this way. We have our LP0 and our NP1, right? So those are our lighting parameters, which we're not going to use yet. So we can sort of leave those to the side for the moment. We have the emit and the NPL both getting sampled, the surface reflected the depth, and then we produce the. Oh, I should also have surface reflect RGB, and that'll just be surface reflect .rgb. And I don't think we need the coverage at the moment because we don't do anything with it. But there is the coverage if we wanted to just be complete in declaring our variables. So this is really what we're looking at here in terms of what we're sampling. And then what we have to do is we have to compile at some point these values. And some of them are going to be pretty easy, and some of them are going to be more difficult to produce. So we'll have to work on that, right? All right. So taking a look at what we've got here, what we want to do is say these texture samples, we want to just sample the textures directly. So we don't want to use a UV. So what we're going to be doing here is more akin to the texture sample from the ZBias program, where we do, where is it? This one right here, where we do a texel fetch. So all of these ones in the lighting transfer here, for example, what we want to do is make sure that these are actually sampling directly from a texture. So they're going to look more like this, right? And so what we want to do is we want to have an IVEC2, which is the place to sample from for the texel fetch. So we'll just do fetch XY or something like that. We'll build this once, and then we'll use texel fetch everywhere else. So for example, here, we've got depth equals texel fetch depth sampler. And we're going to be sampling from MIP level 0. And then we just need to pass that fetch XY in here in order to let it know where we're fetching from. And so the same thing is going to be true in all of these. So in order to get the surface reflect, we're doing the surface reflect sampler. We're going to do it from the fetch XY. And then we're going to do 0. And maybe the correct thing to call it there would be texel XY. Again, just propagate this change down, do it for everybody. And finally, we get the NPL as well. So now we've got all of the data that came out of the original render. We need some way of computing the various quantities we actually need. Now, front emit and back emit actually turns out are quite easy. We have the emit RGB and we have the spread. So what we need to figure out is how the spread's going to be encoded. I think probably the easiest way to encode it is just to say that it's going to range from, at 0, it will go entirely out the back. At 0.5, it goes out the front and the back, and at 1 it goes out just the front maybe. It's hard to say. There isn't really a good way to encode both of them, I don't think, into the range here, although there are some things you could do. You could partition the range as well. You could say that there's, from 0 to 0.3 is back emission only, 0.3 to 0.6 is front emission only, and 0.6 to 1 is front and back emission, right? So there's a lot of different ways that we can encode that, but what I'd rather do for the moment is not get bogged down in that until we actually know what we might want to do with it. So just say like, use this to seed back emitters. So what I'm going to do instead is just say that we don't do any back emission yet. So we just start out with only front emission, and the front emission is whatever the emission was written to be. For the NP, remember the encoding of this, the depth is actually the z coordinate. So the thing that comes out of our depth sampler here is going to be what we need to put in there, although we probably want to, we might want to translate it into something that's more, that gives more information about where in the world it is. But, I don't know that we really need to worry about that quite yet either, because we haven't gotten to the point yet where we really are talking about that particular piece of information and how it should be scaled or stored. But when we produce that NP, right, we know that the depth is going to go in the final part there, and we know that the NX and the NY are going to go in the first part like this, right? Now the NX and NY are actual floating point values here. They're not floating point values when they come in here. And so what we need to do here is we need to bias these back to where they're encoded 0 to 1 at the moment. So what we need to do is actually sort of blow these values out into something that actually represents the range of a real normal, if that makes sense. But I think that's what you're looking at here. That's most of it. That's mostly what we're talking about. I don't think there's really a whole lot else to it. So we really just want to get this working the way that you see it here, and that should be sufficient. So as you can see, we've got a bunch of texture samplers. We've got a query here, but that's really it. So we've got a depth sampler. We've got a surface reflect sampler. Although, there's another thing we could do here if we wanted to. I suspect we could just start, because we're using the layout location syntax, because we are requiring 3.3, we could actually use that for the samplers as well, at which point I believe we wouldn't have to do any of this nonsense anymore. So for example, I think you can just avoid any of this. I think you can just say that sort of thing, right? Where if you want to just specify, once you move up to this level of OpenGL, you don't actually have to bind any of these things that way at all, right? That stuff just goes away, and you don't have to query anything anymore, which is really nice, right? It's just it's a far superior system. And before I thought we were going to do anything interesting with shaders, I was like, well, I don't want to go down that road because that we will require a higher level of OpenGL. But since we're doing nutso stuff in our shaders now, which is always the way, right? It's too seductive. There's really no reason not to do it this way, right? So I think we could also do it that way. And if we did it that way, then when you did OpenGL create program and got the program back, the only thing you would need is the program, which is kind of nice. You don't need to store anything else, and then all this garbage goes away because you only have OpenGL program common, and OpenGL program common can just be handled the same for everybody, right? So that's just nice, right? So we could try to get that working this way. Sure, why not? So if we were going to do that, then what we do is when we do compile depth field to lighting, what we do here is we just say OpenGL program common. and take that result. And so that's really it. All right, so let's move along here. Oops. I did accidentally deleted that. My bad. So now we just need to actually call that compilation phase. So let's go ahead and do that. We need a place to store it, so I'll throw that in here, OpenGL program common. This will be depth peel to lighting. And then what we can do is we can, and one of the things, so maybe I'll show this today too. If we can get that location syntax working nicely, the other thing we can do is simplify a lot of this code as well, which would be really nice for a number of reasons, because a lot of the stuff we have been doing is because we didn't have the option of doing sort of something nicer with the commonality stuff. So we could actually do something pretty interesting here in a second as well. So let's do depth peel to lighting here with our free program, and then we'll do compile depth peel to lighting like so. Oops. Don't need common because there is no such thing. And then off we go, right? So essentially what that's going to do, if it works properly, is we wouldn't have to ever say anything other than texture 0, 1, 2, 3. We wouldn't have to query the location of those or anything else. And the reason for that is just because now that we've specified the location in here, that location syntax will say that 0, 1, 2, 3 is where you get these from. And like I said, I believe you can do that, but don't quote me on that because I maybe have that syntax wrong. So let's see if we can get that working now. Surface reflect sample. That is a typo. It's supposed to be surface reflect sampler. What else we got? That 160, there's a conversion. Where is that happening? Here we go. All right, let's see if that's any better. Oops. Gotta. Okay. Not great. Right? I admit that. This is not looking fabulous if we're honest with ourselves, right? That is not the look we were looking for. So let's so one thing I don't know is whether this syntax is at all right here. Let's take a quick look at the GLSL specification just to see what we are supposed to be able to do here and how we're supposed to be able to announce where these samplers go so that we don't have to do that binding anymore. Let's take a look. This is 1.5. Let me see here. So I'm not sure if there is one of these. I just want here we go. I just want to know how layout qualifiers will work with samplers. So let's see. None of this is particularly relevant to us. Let's see if they say anything in here. They don't. So I want, oops. Here we go. I have a thing which represents the location of the GL context where an object is stored. These binding points, like, okay. So the only question is core in version 4.5. That's not useful. So we may not be able to do that, right? Because this is 4, which we don't require anywhere else. So it looks like we will not be able to use that, right? That's too bad. Like I said, OpenGL 4.5 is actually pretty good. The OpenGLs before that, not so good. And so I never am really, I'm always a little unsure as to what I can use on Handmade Hero that falls within that line. We probably should have just said, let's use OpenGL 4.5 and then use the software renderer if you don't have it or something like that. That probably would have been the smart thing to do, but oh well. So anyway, that does mean that we need to continue doing what we were doing before, which is to make these things all 100% explicit, which is fine. We could try to make program common roll this up, and maybe I will try to do that because there's ways we could make this work, right? So in OpenGL program common, for example, what I could do is if it has a CGL uint here, which is just like samplers. And then what you could do is have a thing that says, well, how many of them are there? And we know that we can't have more than, let's say, 16 in any of our current things because we definitely don't get up anywhere above that. So if we just said, well, there's a sampler count and there's some number of samplers, then when you do OpenGL program common, you would just set that sampler count and it would automatically just query them in some kind of uniform way, right? And then that way, when during shutdown or whatever, you wouldn't during bind time rather, you wouldn't have to write a separate binder for each of these. You could always just use the same binding because it would just loop through the samplers and bind them in order, right? So we could try something like that. If we did something like that, then we could get rid of the sampler bindings. And the way we would do this, I guess, is when we do the create program common, you would just do, where is that? Let's see, compile. Here it is. So when you do OpenGL create program, and it's going through all the results like it does here, what you would probably do here is you just pass the texture handles, the texture names, as like a series of of extras or something like this. Or maybe you just do this, right? So after you do OpenGL create program, that process would then do something like result sampler count equals 0. And then you could do OpenGL, I don't know what you call them, bind samplers, or I guess link samplers maybe is the right way to do it. And then you could just say, well, let's suppose that I have an OpenGL program common. And then let's just say I have samplers. Maybe I'll do it like that. We could do it in even an easier way. Let's do it this way, since it's kind of nutso, but let's just do it this way. Since this is only done basically when you start up the render and isn't something that's speed intensive at all, what I could do is just say, like, look, you can just call this function and just pass them at the end of the function. Then what we'll do is we'll say, all right, let's make an array of sampler names that just has all these in it. And then what we'll do is we'll go, okay, we'll loop over those. And what we'll do is every time we get one that isn't null, we will bind that sampler on the end of the list of samplers. Now, the way we need to do that here, I think you can see, is we need to do, let's see, get uniform location. We need to do something like this. So what we're going to do is we're going to get this sampler ID back by passing the name there like so. And when we get the sampler ID back, what we want to do is we want to see if it was valid as well, right? Because if it's not valid, then we don't want to bother binding it probably. Well, maybe we do, because maybe you want holes in the list, so hard to say. So what we'll do is just say, if you gave us a name, we'll store the value. So then what we do is we say, all right, the sampler count we'll store that into the program itself, right? So this basically just builds up a list there. And what we can do too is we can always assert that the sampler count that we've got is less than how much room we have to store it. So we know we don't accidentally overflow by creating too small a room or something. So there's our sampler linking. And so what that means is now, every one of these things, if we wanted to, could use that sampler linking. Let's go ahead and skip this part of the process for now. So, for example, let's just go ahead and if zero this out for the moment. Here we go. That's 1 star too many. I've already got the array bracket on there, so I don't need that. There we go. And is it prog handle? Prog handle? What's the handle name? All right. And so this should just be what we had running before, right? And it is. So let's go ahead and get all the rest of our samplers, of our programs working through this way of getting the samplers, so that we don't have to worry about that anymore, right? So what that would mean is when we do use program begin, we no longer have to do any of these texture sampler, depth sampler nonsenses, right? That stuff goes away. And what we can do is just say, all right, let's see here. These are all unnecessary at this point, right? Yeah, I think these are all unnecessary. So like this goes away, this goes away, all of these go away. Basically everything that was a sampler goes away. So all of these go away. Right? And we're just left with things that actually are data going into the program. Everything else is, at that point, gone. Yeah. So now, and we can get rid of them here as well, right? So in ZVias program, the samplers go away there. Samplers go away here. The samplers go away here. Here. There we go. And now I should be able to kind of just clean this up via errors. So what we do now is we say OpenGL link samplers. We pass the program that we're dealing with here, which is this one. And then we have just the list of names. So it's not as good as that location binding syntax would have been, but it's definitely better than having to do this every time. So, you know, that's a nice nicety. And maybe, you know, we'll see other people are more well versed in OpenGL 3.x than I am. It may still be that there is a way to do what we wanted to do, so we'll wait for people to chime in about that later. We may be able to get rid of this part as well, but even if we can't, again, this ends up not being so bad. Because at least now it will be handled in a relatively, and you'll have to pardon the pun, uniform fashion. So we won't have to keep writing the code every time. All we have to do is just say what the names are, and that's it. So let's put that down here, and then the rest of these can come up. There we go. And a couple more times for good measure. So nothing there, so it's just these OpenGL link samplers. This is the new one. Here they are. And two more to go. Last one. All right. So I think now we've got all of that stuff worked out. Oops. Don't know why I removed the string names there. There we go. But now all that should be fine. And what we want to do now is just say, when we go to do, because I'm assuming now if we ran it, we wouldn't get anything. Or we get something weird, which is true. What we want to do now is when we do use program begin, the common begin has to loop through and set these, right? So when we come through here and we set up like the arrays, for example, we then have to come through and do the same thing for our samplers. So we just have to do sampler index equals 0, sampler index is less than the program sampler count, and then each one of these is going to be a GL uniform 1i that will be whatever the program sampler's value is here goes to just the numerical sampler index. I think that's all we need, and it looks like we're back to normal now. Let's check the game render as well. By turning off that sort of debug lighting render. That's pretty awesome. That's like the depth value is what we're seeing now. Is that... that's a result, I assume, of the mistake of the port I just made, is we get to view the depth buffer. I didn't expect that, but it's pretty darn cool. Either that or it's just some fogging or something. Anyway, let's go ahead and fix that. That was really cool. I'm a fan of viewing the depth buffer. So let's go ahead and just clean that up there. See if we can fix that. Although I really do like it, so it's unfortunate that we have to fix it. But what we want to do here is just figure out where that, what was going wrong there. So in here we've got, are we still in our ZBias program? Are we still doing things reasonably? Let me just take a look. So we're writing out the surface reflectance to blend unit 0. When we resolve, we're going to be resolving that. So the surface reflectance should be, yeah, should be the right color, should be the correct color there. So I'm not sure why we're getting that issue. Let me just verify that texture sampler and depth sampler go in this order, because I don't actually know what order they do go in. When do we actually use the ZBias depth peel? Let's see, right here. So texture 1 is the depth handle, so that should be there. Yeah, so I'm not sure what's going on with that. And the texture sampler should be the correct one. Now, I don't know, maybe... I don't feel like I should have to do an if on the depth peel, though. I feel like it should work to have these set either way, because there isn't going to be a second sampler either way. So I'm not sure where that's coming from. I am not sure. So here's what I'm going to start with, just because I'm not sure who is at fault. So in order to pinpoint where the error crept in, I'm going to just start by switching what I'm writing out. So I want to see whether I'm failing to fetch a texture here. So in the blend unit color, I'm just going to write, instead of writing out surface reflect, I'm going to write out a bogus value, which is just all red and an alpha of 1. So I should just see a red screen, right? And I don't. So basically that tells me that at least if this function is wrong, it's not wrong in the sense that that it's the sole cause of the problem, for example, right? So something is going wrong a step further. So like in the compositing phase or something like this. So let's take a look at this one in a little more detail here. So let's see what happens if from here, where I'm going to write this out, let's see if the blend unit color RGB, let's see if I stuff that with a red, what do I get? All right, so now I get full red. So it looks like somehow my peel sampler is sampling things oddly, I guess. I'm not sure. Because if these peel samplers were sampling properly from the depth peel... Oh, well, you know what? No. It could be the resolve as well. So the resolve happens in between there. So this, where we have color emit NPL depth, this could be the problem as well. So let's see what order these are in. I think they're actually, I think that's what's happening. I think these are in the wrong order. I think that's supposed to actually be like that. Yeah. All right, so now we're back to normal. Everyone's happy and smiling, and that's just great. Okay. So now I guess my question is, where we've got that location syntax happening, I wonder if we can remove things like, you know, like these values by specifying where they go as well. Because if we could, then we could get rid of a lot of these entirely. Now, as it is, we can get rid of quite a few of them, which is nice, but I'm wondering if we could get rid of them all. So, for example, I can start getting rid of these a little bit by saying that the peel composite program is now just an OpenGL program common. So that goes away. The final stretch program, same thing. And the multi-grid light up program. So again, I'm just taking some time to simplify this down. So let's go ahead and do that. So we really don't need that, or that, or that. Oops. So again, that becomes much simpler, which is really nice. Same thing here. So actually, that can stay that. And same thing here. Okay, and so now when we're doing these frees, anything that was previously calling common that doesn't need to call common, there we go. Very nice. And I think we're still fine, yeah. So the question I have there, again, is can we go even further with that, right? Can we also get rid of sort of the unnecessary, especially on some of these ones here where, like, you know, there's hardly anything getting specified at all. You know, that would be the sort of thing that it would be nice to remove, because they're just, you know, they're creating cruft that's sitting around for no reason. So the question is, would location binding work for these? And of course I don't know. Let's take just one example, which is the resolve multisample program, and see what we can do. So in that case, where we've got the resolve multisample program, where we do layout location equals 0 on this, for the out, you know, is it possible for us to do layout location 0 on that, for example, right? Could I just say that the sample count's going to go at location 0, so when I set uniform 0, that's where it's going to be. And like I said, I don't know if that would work, but that's what I would like to try. And so in here, where we do sample count equals get uniform location sample count, I'm going to leave everything the same. I'm just going to step through and see what the result is. That's all I really want to do there. What's that in? That is in compile resolve multisample. So if we come down here and take a look, it's at location 0. So now let's see whether I can force it to some arbitrary location that is not that. And I can't. So it looks like that is not something that actually works. In this case, anyway. Which is a bummer, but that's just the way it goes sometimes. However, I suppose I guess I'm not sure, like, if that's not what that means, like, why is it even allowing me to make that specification if that isn't what it's going to do? Is that just, like, what's the deal? Or is it because, do I need to specify, maybe I'm a victim of not specifying the right shader version here? Like, suppose I specified version 330 and said location equals 8. Then what happens? Still not. So the uniform location seems unaffected by the specification of where it's supposed to be. Like, that looks like a meaningless thing to specify for all intents and purposes, right? Like, I see no... There does not appear to be any... there does not appear to be any consequence to that value, unless I'm misunderstanding the idea here, right? which is unfortunate. But it looks that way anyway. All right, well, we'll address that a little later. We don't need to get bogged down in OpenGL specifics, because this is just toying with OpenGL. It has nothing to do with anything about graphics, really. It's just the stupid things you have to do to get graphics APIs to do the code you want them to do, right? Like, it's annoying, but it's just how it goes. So let's put that aside for now and go back to what we were doing, which is more what I wanted to focus on anyway. Which is now if I want to call our depth peel import stuff here, let's try and get that working. So I'm going to switch back on the lighting drawing. Don't care about this right now. All right. So happily, this does appear to have imported the lighting values at least somewhat, right? Which is what we wanted. And this is, what is this value here? This is surface reflectance, which is correct, right? That's exactly what we want to see for surface reflectance here. And here's surface normal, which also is looking pretty good, right? So we have plenty of data rendered out now. You can see how like the surface normals kind of like average out, which is kind of funny. Let's see how the other values average out there. There's the surface reflectance kind of averaging. And it seems like our averaging process is kind of busted, which I think means we're going to have to be more careful about that relatively soon. But you can see, for example, like if we just look at the surface reflectance here, there's really no way that you should have such a discrepancy based on movement. So our averaging down, you know, isn't great at the moment, right? It's not, and I think a lot of that, again, has to do with the uneven sampling. So we probably want to fix that at some point and try to get something that's going to be a more reliable downsample. Because that will make our lighting be really inconsistent, and that's one thing that we're going to have to work on for sure. Okay. But either or, we are able to do our little sphere light here, and we are downsampling it properly. So now we've kind of got that part of the lighting, that kind of in pass, working correctly. And so what we want to do now is we want to basically do some work with actually bouncing that light around. And the way that we were going to do that, which we haven't played with yet, right, is we have the import phase, which is really just responsible of converting values from the depth peel system over into something the lighting wants to use, which is basically an unpack, right? It's taking some relatively concise information that's packed into 8-bit values, and it's blowing it out into big 32-bit values for the iteration process. We have the upward phase, which is doing our sort of downsampling. It's not very good right now. Like I said, that downsampling creates some artifacts. So I think we're going to have some problems there, and we're going to have to beef up what this upward phase does, assuming any of this lighting stuff works the way it does once we sort of get it into a more real sense. But then we've got the downward phase. The downward phase is really the thing that was supposed to do some of the lighting calculations and right now isn't doing any lighting calculations at all. So what we need to do is make this downward lighting phase actually do some lighting transport, because that is the problem with the current thing that we're doing, which is why it's not actually producing any lighting, is because we're not actually ever running the transport equation, right? All we did was get the sort of procedural trappings in place to get the data we needed for lighting and to have a process we could use for lighting. But now we have to actually put in some lighting equations, because without those equations, we're not really using the computational framework to produce anything valuable that looks anything like lighting would look. So that's what we want to get started on right here. So taking a look at what we are doing, we can get rid of this if one well, I guess we'll leave it there for now. We probably want to have some switches we can turn on and off dynamically as well at some point. That would probably be a good idea. But let's go ahead and pop over to the actual code for the compute down lighting. And so we can kind of see here, this is the code, multi-light down. And so the way that you can see this working is we already did the lighting query. So you can see here we set ourselves up to sample all of the information that we wanted, and we sort of sampled things nearby in the texture and all that other sort of stuff. But we don't actually do anything now with the result, right? We don't actually, like, we've got this transfer light call, and what you can see is the only thing that transfer light does is it just averages the light together, right? Which is like a completely, non-lighting. It has nothing to do with how light should actually be behaving. So presumably what we would like to do here is we would like to do something that actually transfers the light based on some kind of lighting equation of how much light there should be flowing from one place to another. Now, the issue here, we got to start to think about like how we really want to do this for real. And what I was talking about before in terms of the let's see here, Milton. Hello. There we go. So if you think about what's supposed to happen here, like I was saying, there's one kind of sort of straightforward way to do it, and that's a little more costly and difficult. And then there's one way to do it that was sort of the multi-grid thing that I was saying is kind of a harebrained scheme that we might have to just jettison because I don't know if it's even semi-plausible. But if you imagine looking at sort of a subdivided space here where this is the entire lighting information grid, let's say, at the highest resolution. So we know stuff like, oh, there is a bright light right here. Like we have that information encoded in the bitmap at a very high resolution. But, what we can't do is for every pixel on the screen, we can't step through every other pixel in the lighting buffer, right? We can't step through 1920 by 1080 light informations and calculate whether or not we can see that particular light, right? Because in order to do that, we would have to step through all of this stuff and see whether we could see it or not. And furthermore, even if we didn't do that, we'd still just have way too many to do, right? So it's not feasible. It's not a feasible thing for us to do at all. So if we actually imagine looking at a lighting sample and we want to do something like figure out whether or not we can see particular lights, then what you could imagine us doing is sort of a multi-resolution query where we did something like, okay, let's take each of these 4 large regions, let's say, and we'll say that the one large region we're in maybe we'll treat more specially, but say, for example, this large region here, let's just assume that that large region is only going to give one sample. So everything in here has been averaged together. Same thing with here, same thing with here, right? And then we're just going to compute the lighting to each of these large regions rather than to like every little individual thing inside the region, right? That's kind of the idea that we're going for here. And in order to do that, I think what we want to, what we would want to say is, well, okay, we know that we can see each of these regions if nothing is in the way in our smaller region, right? So what we would want to do is take subsamples like here, here, and here of how much sort of blockage there would be, how much shadowing there would be of stuff that comes through. It's kind of what we want to say, right? So you can imagine this multi-resolution process where we want to be able to do that basic operation. And you know, the multi-grid dream here that, again, I've said many times is a harebrained scheme, so I don't honestly believe it's ever going to work. But the harebrained scheme was that we could come up with one kernel that you could apply at each step of the multi-grid that would just propagate approximate results of this process down so that you only ever did one of these. So for example, let's suppose that the thing that the thing that we want to do looked something like this, right? So we're taking a sample here, and actually since it's multi-grid, let's say there's well, no, I guess we'll do two levels at once. Let me draw this a little bit better. So let's suppose we want to compute the lighting here, and let's suppose we want to compute it from the entire neighboring region, right? So we know that there's going to be 8 texture samples, right, that we would have to take to find out what the data is in these regions around. Then internal to us, right, this would give us how the incoming lighting flows in if there was no shadowing. But we know we probably want some shadowing, otherwise the lighting solution is not going to be very interesting. And so in order to do that, what we would have to do is say, well, let's subdivide ourselves, right? And let's do the same thing again. And what we would want to do is say, well, okay, let's see how much of a shadowing there would be if we were trying to look at these things. So looking out at 3, looking out at 0, looking out at 1, looking out at 2, 4, etc. How much shadowing is there in our local, slightly more local area? How much shadowing is there to be able to see these things that are further away, right? And so you would end up taking 16 samples for every one resolution here that you wanted to do, and then you would use those values to sort of figure out how much lighting contribution you should add in the region you're currently operating on. And so, you know, this actually sounds like plausible, like vaguely plausible. But that's the primary operation we'd have to do on the downsample. And when we did that downsample, we would then add that lighting result, whatever we got from each of these 8 computations, right? Each of those 8 computations would tell us how much light to add to the result we're standing on, right? The result that we're actually computing about. So, yeah, that's really all there is to it. So the one thing that we don't currently store, and I feel like we kind of do need to store it, as much as I hate to have extra textures, I think we probably would, is that one of the problems we have right now is we're always assuming that things are at the centers of their grid cells, and the only thing that we check is the height. But we probably don't really want to do that, right? We probably want to bias. We probably want to say that a cell contains a point, and the point is the location that's the averaged amount of the lighting that's coming out of it, right? Or the average location of the occluders in that area, right? So we kind of have two things, you know, like I say, that as we sort of develop this, we've got to kind of think about what we really want to store. and how we can make something that's going to be useful in that way, right? But anyway, so let's suppose that we had that. So we augmented this by at least one additional thing that we don't have right now, which is just the position. Because right now we do have the depth, but we don't have the position. We can assume that the position is in the center of the cell for now, but that's not a very good approximation, because it may be that like there's a very big wall here that's really what we want to talk about. So it gets kind of difficult to think about how those sorts of things should be happening, right? And furthermore, it strikes me that, like, again, it seems almost like in order, if we really do want to try to push this multi-light thing and see if it really does, a multi-grid light thing, and see if it really does work, it also strikes me that we may have to store two separate things. We may have to store, like, the light and the occluder differently, or maybe store them on the up pass and the down pass differently, I don't know. But that part is just a little tricky. And I don't know if I don't really know what the way around it is. Well, I'm getting ahead of myself. So anyway, if we just assume we just start with what we have right now, that's basically the computation sort of thing that we would need to do, right? We would need to be able to do this sort of light transfer. Now, whether or not we need the diagonals, I assume we need the diagonals because otherwise you kind of get this weird, your lighting will have very heavy sort of axial components. So I'm not sure you can really ignore the stuff that's coming from your sort of diagonal neighbors. But who knows? So right now, all we're sampling is the cross, and I think we may have to sample sort of the diagonal as well. And so right now, we also aren't doing any shadowing, so we don't sample the subcross on the next level down either to figure out what kind of shadowing we're going to be doing there. So again, a little bit confusing and a little bit complicated, but that's sort of where we're at, right? So what you can see here is we have a front emission and back emission that we're going to compute because we're pointing a particular direction, and we collect light on our back and the front and back of our surfaces because we are a sprite cards thing. Normally we'd only have front, but because all of our game is like these little cards, it seems sensible to treat both sides since everything's infinitely thin. So taking a look at the transfer lighting question here, you can see that we do a transfer light and we say, here's our reception parameters, right? Ref P, Ref N, Ref C, and here's our emitter parameters. So without doing any further work, we can do the light transport here in some way that's something other than just a straight average based on our normal and things like that. So we can actually do something there. The thing we can't do is the shadowing, because in order to do the shadowing, we have to be able to sample what would be in between us. Now, maybe we can just have the transfer light equation sample something that's in between the two positions and try to do something smart about that. That is something we could add, where like that's where that sampling occurs. But for right now, I'll just try doing just some basic transfer. So because this is so approximate, I'm not going to start with anything that's even trying to approximate real lighting transfer. Instead, what I'm going to do is just see how much these two things can see each other, right? So since we want to do this transfer light, what I want to do is say, okay, if I've got two surfaces and I want to know how much light they're going to bounce to each other, at the very least, something I'm going to have to do is how much are they facing each other? Right? The cosine of the angle between them is going to be important here because if, for example, I'm talking about two surfaces that are pointing away from each other, then no light is transferred. So I have to do some kind of computation there. So the first thing I want to do is figure that out. So I'm going to introduce a facing term here, and all that's going to be is that's just going to be the inner product of the light normal and the reflection normal. Now, the product of those two we want to condition the result of that because the condition of the result of that doesn't come out in a way we can use for multiplication very well. Why doesn't it? Well, it doesn't because if you think about two surfaces that are pointing the same direction, here's my reflector, here's my light. If I have these two surfaces, I want to say, well, how much light transfer between them? The answer we know here is none, right? The answer is 0 light is transferred between them. But the dot product of these two, right, to get the cosine of the angle between them, the dot product of these two will produce 1 because they're pointing the same direction. So what we want to do is do sort of conditioning of this value. If they were pointing the way we want them to point, their value would actually be -1, right? Because they're pointing in opposite directions. So what we really want to do is we want to negate this result, right? And I don't remember, sorry, I know we did a bunch of pound defines here. Here we go. So we have inner, we have clamp 0, 1. Okay, good. So basically what I want to do is say, all right, let's take the negative of this and clamp it like so. And so what that gives me is a value from 0 to 1 that just says how lined up these two light sources are, right? And I can use that to now attenuate that result, right? I can use that to attenuate any lighting transfer that's going to happen between them. So now we also get into the how far away they are, because these are diffuse surfaces, not specular at the moment, although we may want to do some work with that obviously in the future. What we want to do is take the light emission and we want to scale it by that distance as well, use the inverse square law there. So the distance between these two lights, light P minus ref P, we really want that to be squared. So this is a length squared computation. That's going to be modulative as well. So as that distance goes, I want to be 1 over the length squared there. As they get further apart, I want that to divide out, right? So if the distance squared were 0, that should never actually happen. So I think I can avoid that case because we're always testing cells that are, there shouldn't be any way to actually have them become 0. We'll have to see if that's true, but that shouldn't happen. So we know that we also have sort of the fall off term, which is going to be 1 over that distance squared. Now somehow I never did define some of these, it looks like. So, length and a length squared of vectors. So the length squared of a vector is obviously just the dot product of itself. I think there's a built-in for length. Here. I don't know if there's a built-in for length squared. I'll check. But like I said, it's just the dot product anyway. Yeah, so there you go. Length is, there's no length squared. So just dot a vector with itself. That'll give us the length squared, so that's all we really need. So if we want the length squared of this vector here, that's what we'll get. And I think that's all we really need to know. So computing the lighting here, if we want to start by making something a little more sensible, then what we want to do is do something like, okay, there's the facing times the distance squared times the color times the emission, right? So then we've got something that takes into account the angular aspect of it. We've got something that takes into account the fall-off distance aspect of it, and off we go. Problem with this, although that's all well and good, is right now we are not actually reconstructing the position in any way that makes any sense. So we have to be able to take fragment coordinates and translate them into positions, and right now we don't have any way of actually doing that. So that's going to be a whole situation kind kind of a whole what's the word I'm looking for? That's going to be a whole bailiwick. It's in and of itself. Am I losing that term correctly? Spelled it wrong. I guess I kind of used it right. You know, it's not. I wasn't a fabulous use. This is not one of my finer vocabulary moments, certainly. If we're being honest about it, but it's all right.
Bailiwick.
Bailiwick.
Bailiwick. Bailiwick.
So bailiwick, I pronounce it very old. I pronounce it late Middle English, which is not good. So bailiwick. That's going to be a whole nother bailiwick. So yeah, so we can put that transfer lighting in there like so, but what we're going to find is this is going to blow up immediately because the length squared term that I said could never be 0 will actually be 0 a lot of the time because we're artificially making all of our positions be exactly the same, which is not good at all, right? That is the opposite of what we want, and so we need to have some way of making this result here make more sense, right? So we can start by using the UVs, but that's not going to be at all correct. And so we need to create a better, some better work there, right? All right. So let's start by, oh dear. I don't know why. Sometimes we get a very low frame rate, and I never really know why. I think it's like we're pushing this graphics card a little bit beyond what it can really handle. And our undamped spring here is not particularly happy about that. So I wonder what is just literally that, or is it just the fact that we were, is literally just the fact that we're doing some more operations here enough to really slow things down? It seems odd that it would be really that painful for the card. Is that actually the case? So it's not, it's just that slow at the moment for reasons that are not immediately clear to me. Granted, this graphics card is extremely old, so it could be any number of reasons, but we don't have a lot of ways to profile it at the moment. Let me go ahead and put that in here. What I can do is I can fix sort of the underdamped springiness, I suppose, of the body-head dichotomy there to prevent it from causing the problem that we're getting there. But that's not going to help us keep a reasonable frame rate that we can actually use for testing is the only problem. We can reduce the resolution to something very low, like so. And that definitely looks better. All right. So that's good enough for now. I'll just live with running at a low resolution for this particular problem, for this particular situation. All right. So again, so this brings us back to, again, the sort of place we're at. In terms of lighting transfer at this point, right, we need to now start having our lights be brighter than 1 as well. Because as you can see, when we get out to here, the lights are so dim at this point as well, because we haven't encoded them in any sort of way that makes sense in terms of the visible area. So we probably have to take a look at that in a second as well. But let's just take a look at what our other values are for now. So our lighting reflect color seems pretty reasonable, you know. I don't think we're going to have a lot of problems with that going forward, right? That seems pretty much fine to me. And let's go ahead and take a look at our normals. Again, yeah, the normals seem to be pretty sane as well, right? So I think we've got those two in a place where they're not going to cause us too much trouble. So it's really just the lighting transport part that we should be able to focus on getting something out of at the head end. So the first thing that I want to know is, can we get an actual light in here instead of just straight up red? And I don't remember why we ended up with straight up red. Was that just because we had placed a bright red light for no reason into the compile zbias program where it was using light P? Yeah, so I'm going to go ahead and change this to a white light at first because I want to see how it interacts with the reflection color. Because something is weird at the moment and we have to, so that's the first thing I want to debug. So if you think about what's happening here, this is the actual result of the light transport. It doesn't make a lot of sense because if you look at what's happening to it, we should be seeing some of those colors start to come through at some point. Now it makes sense that the part we can see directly, so the part that's not going to have any bounce, it makes sense that that would be bright white because again, what we're seeing there is just clipping off the end potentially. Now we could do some work there to make sure that we do sort of our tone mapping at the end, which is something that we do have to do. But we should be able to start seeing some bounce of light soon that takes into account actual colors and stuff like that. But we're not seeing any of that. So we're kind of just like not correctly doing anything at the moment. And I'd like to know why. So again, one thing that I do want to do is crank the power of that light up a little bit. So when we are transferring the light over, so when we do depth PL to lighting, I want to scale up that surface emission. So the emit RGB here, for example, I'd like to take the maximum light power. And that max light power is just some arbitrary value that's how strong we want the strongest light to be relative to the 0 to 1 range, which is just reflected light, right? And so if we do that, we now have, like, this light is very, very bright. So when it kind of gets blended up, yeah, you can see it should always tend to dominate anything that it blends with, right? Very powerfully, which it sort of is, which is good. But what I don't understand is, like, if this is the top level version, how come we never see almost any light bleeding at all, right? So we never see any light transfer happening. And why is that, right? So I've got some issues in here to address. So let's start with the individual terms. And again, all of these variables are kind of bogus, so it's kind of hard to start with. It's sometimes hard when you're just trying to start up because you don't have everything worked out yet. It's hard to know what's actually incorrect. But what I can do here is I can say, well, what if we turn off some of these terms? So suppose I turned off the fall off and the only thing that we used was the facing direction, right? What would that do? And what you can sort of see here is not much, right? So the fall off term doesn't seem to necessarily be a huge culprit there. What happens if I turn off the facing term as well, right? Again, nothing. So it's almost like our lighting transfer is never transferring anything. Oh, that's good. That's a nice typo. Try that one more time. That would explain it. There we go. Okay, so that's more what I would expect to see. So now let's try turning on the facing direction. So now we're going to only transfer based on facing directions matching up. So you can see that's not really working, right? So facing direction, not working. So we got to fix that. And let's see how fall off looks so far, which is, again, going to be kind of really bogus at this point. But all right, so fall off term, not a problem. That's not knocking things off. However, it does seem to be boosting the light power, which is not what I would have expected, because it should strictly diminish. So I guess what that means is our distance squared is, yeah, so our distance squared, it's supposed to be coming out from the light. So really what we want there is, you know, more like this sort of thing, right? We never want it to increase the power of the light if it drops below a certain amount. So we always want it to sort of diminish the light as it goes outwards, right? So if we're trying to diminish the light as it goes outwards, again, the fall off rate here is going to be also based upon what our units are in this sense, because that value will get bigger faster depending on the unit scale, right? So this computation has to be made correct at some point. But we can, again, hack in whatever we want here. If we want more distance attenuation, we can hack in something to give us more distance attenuation as we go, right? So if we want to play with that value, right, we can play with that value. So there's some more distance attenuation, right? And if we look at what's happening to these, you can kind of see how that light is spreading out and where and when it's sort of spreading itself out, right? So now let's figure out why our facing direction isn't working at all. So we have the light normal and the reflected normal. Maybe those are wrong, would be thing number one. The other thing is we do the inner product and then we negate it. Are we sure that's right? I believe it is, because again, the light normal and the reflected normal, the maximum transfer should be happening when they're pointing opposite, which is when it'll be -1. And we want to clamp that between 0 and 1, because if it's negative after we do the reversal, that means they're pointing away from each other. We don't want to use that. So when I turn this on and we use the facing term, what you can see here is it immediately kills all of the transfer. So what that suggests to me is we must have a problem with how we're packing our normals in or unpacking them. I don't know. But something's not going right. So when we do reconstruct normal, you can see here what we do is we square root basically just the two terms that we have to make sure that the result sums to 1, and we stuff that into the normal that we're using, right? We got the MPX, the MPY, and then the Z. So that should, in theory, compute reasonable normals. I don't know why it wouldn't. So the question is, are we sampling them correctly? Are we getting them wrong some other way? And I don't know. So when we're doing the light samples for the left, right, up, down here, and we're getting, these parent samples, what does that look like? Well, here's our front and back emission. Here's our texture sample for the NP value, and we construct the normal from that NP value. It looks sane. I don't know. I don't see what the problem would be there. Yeah, I really don't see it. And I can understand a lot of things are pointing upwards, so I can see why there would be less transfer when that happened, but it shouldn't be none, right? It should attenuate but not completely eliminate I would think. And that's not at all what I'm seeing. So I feel like that is still a little bit busted. And we're not really getting good UV values out. Now, what's weird about that, or sorry, good normal values out. What's weird about that is this does look promising. Like that looks like a thing which I haven't sat down and tried to figure out if it's exactly right, but it does look roughly like a plausible normal map, right? And so the weird thing is, if we're sampling from that, we should end up with some reasonable normals. So what's going wrong? I don't know. Because the x and y's of the position are definitely wrong. So if there's one that's going to be more incorrect, it should actually be that one. The normals actually should be right. We're not hacking the normals at all right now. The normals are 100% passed through the pipeline, and so it's just and we're viewing them too, and they look reasonable. So I'm not sure why we're not getting something plausible out of there. Now we are sampling from parent NPTech and our NPTech. And I suppose I don't know if maybe one of those is coming in wrong. We wouldn't know if it was. So I suppose we could just double check here to make sure that like all of the samplers are set up properly. But it sure looks like they are here. And if I go look at when we actually do this setup, let me just verify this. If I open up a second window into this program here, this file rather, can I get some confirmation that we're specifying these buffers correctly? So 0 is the front, 1 is the back, 2 is the NPTech, yep, 3 is the surface color, and 4 is the NPTech as well. Again, all looks pretty reasonable there. That's what we would expect to see. So let's do this. Let's write the reconstructed normal into the channel we're not using, which is here. So let's just see if we're querying the reconstructed normal correctly. So here's that buffer. Here's us querying the reconstructed normal. So this is, an x, y, z of the normal itself. And we can sort of see whether this makes any sense. Unfortunately, this isn't really packed in any kind of sane way because now we've got like negative values. We've got negative and positive values in here, floating point values, and how those are going to get mapped to a display is kind of like, well, what I have no idea what it's going to do with the floating point of a negative value. But at the very least, what we can see here is it's not ludicrous, right? It's at least plausible. Now, looking at the individual values themselves, there are some things here which, again, don't seem to make a lot of sense. So maybe there are some problems here that are bad. So for example, I'm seeing gray where things should be pointing upwards. And once we've converted our normals into actual real floating point x, y, and z, then we shouldn't see gray for pointing upwards. What we should see for pointing upwards is 0, 0, 1, correct? Which should be blue. And that's not what I'm seeing here, right? So I feel like I should be seeing blue where I'm seeing gray. Similarly, like something like the hero where it's pointing in negative y, I suppose that makes sense because that would be blue and red would be set and green would be negative and not visible. So that seems fair. So it really just feels like the z value is kind of wrong. Everything else feels like it might be correct, but the z value does feel kind of wrong, potentially. So let's see. Why does the z-value feel wrong? Well, let's suppose that I was to blast the z-value. So let's just overwrite it with 0 and verify that I'm seeing that correctly. Right? So there's no blue. That's right. That's what we would expect. But you can see why I'm having trouble with this. Looking at this screen, I'm seeing things that are facing upward are somehow showing red and green components. They shouldn't be, right? Things that are facing upwards should be showing 0, 0, 1, and they're not. So again, I've got a problem somewhere in the pipe here. I don't know what it is, but it's definitely there. And that's the bottom level that I was looking at there. And so that bottom level should in theory be the result of the copy, right, as well. So that's just kind of troubling. So I don't know what's going on there. Let's take a look at how we're writing out those values when we do the depth field lighting. Let's make sure they're right. So the nx and the ny are straight up scales of the incoming value, which is just the x and the y, right? And then the x and the y of the normal, we're just scaling them into the -1 to 1 range, right? Which is what they should be. No, that's not true. I lied. So it should be -1 plus 2 times the value. So that was just a typo there. All right, let's see if that gives me anything better. In this case, much better. Much better. That's what I want to see. Okay, so let's stop blasting the Z now. I think we figured out what was happening there. Where's my transfer light down? There it is. Let's go back to showing the right thing. And now can I see, do I have, there we go. So that's what I wanted to see. That's exactly what it should look like. So now I have more confidence that my normals are at least, plausible now. Like that looks much better. Good. Okay. So now what we need to know is when we do this sort of light transfer bouncing around this, my question is, when we do the transfer light, why are we not seeing anything when we use the facing direction term? Because even if it was fairly low, we should still get to see something, right? And so I don't know why we're not seeing anything. We can stop writing out the normals here now because I know that they are not the problem. What I could do is take a look at the light normal. So for example, I could look to see what we're getting in left.n. Which is just the leftward light sample. And now I can just see what is that. So there's the leftward light sample. And again, the leftward light's normal. That looks fine, right? That does look like what I would expect it to look like. So again, I'm just not sure why I can't get any transference at all. It makes sense why there's not a lot of transference because again, we're sort of at this in this way where we have our sprites are mostly facing upwards, so it's hard to get some transfer going there because of that difference. But what we could do too there as well is we could say, we could take, for example, the level geometry and maybe bias it a little so that we would see some, so that we'd have bigger walls nearby, right? So that's one thing we could do. But again, I just feel like it's a little weird that nothing is coming through still. It just doesn't seem quite right. And so since those normals are all relatively valid, I guess what I'd like to do is let's take a look at the inner product as just something we can write out ourselves. So suppose we were to take the negative inner product. I won't even clamp it yet. Let's take the negative inner product and just write that out. So what is the actual negative inner product of the screen? What don't you like about that? You don't like that that's just a regular value. Okay, that's fair. I want to replicate that out. Is that something I can do like this, for example? Okay. So here's that product. And it barely has any result anywhere, right? Which ain't great. Let's take a look at the non-negative version. So there's the non-negative version. So here is we're basically looking at when you just take the two normals next to each other and you dot them together. What do you get? So again, in some sense, I can see why that would be the case. Because when you have a bunch of normals like pointing all upward, they're not going to transfer light like at all, right? But at the same time, when you have like this part here and that part here, they should. And I guess that's where I was getting some of that, though. I'm supposed to be in the Q&A right now, aren't I? But, I mean, I'm getting so little of it. Can it really be that little? I guess it could be. I mean, it's not out of the question. I mean, one of the things that is true is that lighting transfer doesn't happen much along the ground, right? Like ground to ground lighting transfer, if there's no hills, doesn't happen. So it is kind of true that I'm sort of setting myself up for failure in that I'm expecting light to transfer between two things where no light should actually transfer. Let's go to the Q&A. We'll pick this back up tomorrow, but I don't want to use up all the time that might be used for Q&A. There we go. Let's just get a little bit of Q&A in there. Because, yeah, that does seem like it could be plausibly true. So I should have to... yeah, I should have to think that through a little bit further. So we'll see what we end up deciding tomorrow. Miblo, could some of our lighting code end up being used by the audio system to figure out where and how obstructed, reflected sound sources are? Probably not, because since it's on the GPU, since it's on the GPU, I don't really know that there's going to be there's really not going to be any way to like get that back, right? We'd have to like round trip it. So I don't think it's probably something we would want to do that way. You probably want a simpler thing that can run on the CPU. Lord of Six, try 1 minus clamp. Well, what are you suggesting that would do? Why would we do 1 minus clamp? So, you know, what we want to do is have it so that as these things turns towards each other, right? So as these things turn toward each other, we want the value to go up to 1. And so that is the, if this is A, this is B, that is A transpose B negated, right? That's the negative of that. So if you are going to clamp that value, and it's going to run between 0 and 1 for how close they are together, inverting the range is going to make it so that this is the highest lighting transfer, right? It's going to be the perpendicular that's the highest. And that just doesn't... That's not what we're trying to accomplish here, right? Like that's not going to help us get towards a functioning lighting system, because like we know that it's definitely not the case that perpendicular surfaces transfer the most light. That's not the case, if that makes sense. SF Gardner, should you add a fake ceiling for lighting or a non-fake ceiling based on the floor above the current one? Yes. I do think we should, but the problem is how to do it. Because the nice part about the depth peel renderer is it does give us like all the floors, but it doesn't give us the one above the one we're on that's completely invisible. So it's like, not entirely related to today's stream, but will you perhaps use something like a pipeline state object for binding resources? No, we probably won't do anything like that. Basically, we're pretty much done with any sort of fussing with the pipeline management, I think, at the moment. Like it's pretty much probably will look the way that it looks right now. And yeah, my assumption is just that, yeah, like, so we'll have to see, but in order for it to do the lighting transport there, we may have the problem of how do we get some values in that are multi-level, so we can have like a ceiling, like we were saying. All right, folks. I think we are done for today. But we'll pick this back up again tomorrow. All right. Thank you everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can follow along with it and do your own experimentation. Maybe you can come up with some good light transport stuff. We also have a forum site where you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot that tweets the schedule so you know when we're live if you want to catch us live, and episode guide for catching up on old series. That's it for today. I'll be back tomorrow to play around with the lighting a bit, see if we can get some reasonable light transport stuff happening. Yeah, then that's about it. Until then, have fun programming. I'll see everyone on the internet. Take it easy, everybody.